Hello, good morning. Thanks for coming. We have Project Huayra, or Team Huayra. Okay, so those of you who don't know what Huayra means, who knows what that means? Nobody knows. It's Inca god of wind, am I right? Or a racing car in Italy?
Yes.
Okay, that was interesting. Go and read about it on Wikipedia. They designed a turbocharged engine, and they built it. So, introduce you to
All right, good morning, everybody. We are Project Huayra. My team members are myself, Detail Control System, Anthony Bianchi, Ryan Arnold, Chloe McBride, Ashley Villa, and Dylan Benshaw. So kind of to start us out, I'm just going to go over a general presentation overview of what we'll cover today. First of all, I'll be discussing the project description. Second, our subsystem design. Third, the testing that we performed. Fourth, our safety that we integrated into our project. And fifth, some of our conclusions and recommendations. So first of all, the purpose of our project. Currently, we do not have a working engine model on campus. So in order to fulfill that void, we would like to create a propulsion demonstration and test unit. And this will help us to see measurements and calculations in real time that we learn in our coursework. So this turbojet engine is an air-breathing Brayton cycle in a jet engine. This is designed to produce thrust, and in doing so, it has hot, high-pressure gases that spin a turbine in order to drive a compressor. So this is our overall system design. On the left is our CAD workup, just more of a clear model of what we imagined before we started building. We have 4 main components. The first of which is the turbocharger. This is a commercially available unit. The fuel system, also commercially available. The oil system, which consists of a few commercially available parts. And then our combustor, which is our major design component of this project. This was all made in-house here at Embry-Riddle. On the right is our fully assembled unit, which you see in front of you, minus the wires. And I will now hand it off to Tony to talk about the turbocharger.
Thank you, Heather. So for the turbocharger for Project Huayra, we decided to use a Garrett GT3782. This specific turbocharger has a 3-to-1 compressor pressure ratio at 110,000 RPMs and 76% compressor efficiency. These values were pulled from the compressor map that you can see here on the right, provided by Garrett Turbos. For basic turbocharger operation, air first starts at station 1, which is the inlet stream, and then is drawn to station 2, which is the compressor rotor. Here at station 2, the air is spun radially and tangentially outward and captured by station 3, which is the compressor scroll. Here at station 3, the air is sent out of the turbocharger to head to the combustor to be heated. Station 4 is the turbo bearing housing, which I'll discuss more in just a minute. Station 5 is where the air is coming back into the turbocharger from being heated in the combustor, and it is captured by the turbine scroll. Once it's in station 5, it is then expanded through station 6, which is the turbine rotor, and exhausted out of station 7, the exhaust stream. I'll now talk about the oil and plumbing systems for Project Huayra. For the oil system, we decided to use a recirculating oil system, which means all the oil in the system will be reused once it reaches back to the oil tank. You can see here on the right the flow diagram for our oil system. The oil will begin in the oil tank and be drawn to the oil pump. From there, it will be pumped through the oil filter and to the top of the turbo bearing housing. Here in the turbo bearing housing, the oil flows over the turbo bearings and cools and lubricates them as it passes through. From there, the oil is then sent out of the turbo bearing housing and drawn back to the oil tank. And then the process will be started once again. For the main components in the oil system, we decided to use first a 5-gallon vented oil tank. We decided to use a vented oil tank because that allows all the work put into the system by the oil pump to go in the flow rate of the oil rather than pressurizing the system. This is important for our application so that we can have the most amount of oil flow rate over those turbocharger bearings to dissipate any heat that is built up. The next main component is a 3.7 gallon per minute geared oil pump. We decided to use a geared oil pump because the inside components are made out of brass gears rather than plastic, which would begin to yield at our expected operational temperatures of around 250 degrees Fahrenheit. The last main component we use is an inline oil filter. This oil filter is very common to automotive use oil filters and is really just in the system to clean the oil and make sure there's no buildup of any material in the system. For the oil in the system, we decided to use an OW20 full synthetic motor oil. We chose this oil because it has low viscosity at lower temperatures for startup, which is where most wear happens in the system. It also maintains its viscosity at our expected operation temperature of 250 degrees Fahrenheit. We chose full synthetic motor oil because it performs better at our expected operation temperature of 250 degrees Fahrenheit by resisting coking or breakdown of the oil better than organic fuels. It'll also have less severe solid carbon deposit buildup over the operational life of the engine. Now for the plumbing system. To contain the airflow leaving the compressor heading towards the inlet of the combustor, we decided to use 2-inch steel piping. For the oil and fuel systems, we use 3/8-inch flexible aluminum tubing to contain those working fluids. To connect all the components in the plumbing system, we decided to use 3 main types of component integration. The first of which being a flexible silicone rubber boot with adjustable hose clamps that you can see here on the left. This allows a degree of flexibility in the system and still seals all the airflow. The next type of component integration was a V-band flange and clamp. We used this to connect the exit of the combustor to the inlet of the turbine scroll. The last type of component integration we used was just a common 8-bolt flange that you can see here, connecting that 2-inch steel piping to the inlet of the combustor. I'd now like to hand it off to Ryan Arnold to talk about the combustor.
Thank you, Anthony. All right, so let's break down the combustor more. So the combustor was designed with these parameters in mind. The most important being the fuel-to-air ratio of 0.0176 pound mass of propane per pound mass of air flowing through the combustor at all times, which would lead to after combustion an operational temperature at the exit of 1340 degrees Fahrenheit. And the type of cooling is film cooling, and that keeps all the hot and components cool, and so they don't go overheat and yield and hopefully melt sweet. So here's an overall CAD file of the design, CAD being used because it can show all the components side by side and exploded. So from left to right, we have the conical inlet, the flame tube, which actually houses the combustion process, the casing that routes the cooling flow, and then all of that is channeled straight to the turbine scroll inlet, where it goes to the turbine. So to expand more, the conical diffuser is a 9-degree divergence angle tri-path design. So every section you see between here, and here is all 9 degrees, and that's known as the sweet spot to minimize both stall losses and also for friction losses through the system. The geometry works out so that way it's about 9 inches in length, and then the 2-inch inlet size is so that it can interface with the compressor outlet right here. And then it expands to the outlet size, so that way the flow is properly slowed down so a stable flame can actually be held. Here's the flame tube and the casing. They're tubular in style because they're much easier to manufacture. The casing is 6.36 inches in diameter as well, so that way that it can be made straight to the inlet. And then the flame tube is 4.5 inches diameter, and this geometry is there for reasons that I'll explain later on. So there's a couple of main components in the system. The first being the swirler and the impinging jets. The swirler is here. Excuse me. There we go. All right, it's right here, and then the impinging jets you can see are Jesus. All right. Well, oh my goodness. Either way, I'm sorry about that. The jets impinge in the holes that you can see inside the flame tube, or on top of it rather there. And the swirler acts to swirl the flow helically, so it'll go in like a tornado shape essentially. And then the impinging jets will impinge and send some of the flow forward, and then some of it will recirculate, and that will then that will make a toroidal recirculation zone, which is donut shape, and that can house a stable flame. And then the film cooling is done gradually, so there's actually not a dilution zone in this flame tube. Every small hole that you can see is for film cool, and then there's no larger holes on the aft side of the burner, and it gradually cools and dilutes as it goes. And then there's also a flange that's incorporated at the aft section that will bolt straight to the casing. Here's the swirler that's more in depth now too. The vanes are machined at 70 degrees, which will incite a swirl number of the flow of about 1.2, which is above the critical number of about 0.6. The transition cap that houses all of this is slotted as well, as you can see on top there, and that's to cover the primary zone, which is the hottest part of the flame tube and cooling flow, so that way it won't overheat. And then there's also a 1/4 inch slot cut for the fuel ring to maintain the placement inside of it. The fuel ring itself is shown here. It's made of 1/8 inch stainless steel tubing that is welded off on the end with 8.0552 inch holes drilled into it with a carbon drill bit, so that way they're nice and clean and smooth. That corresponds to a size number 52 drill bit. And then the holes face the swirler shown in the previous slide, so that way the fuel is injected and then pre-swirled, and it's mixed properly prior to being burned. And these holes were sized based on the mass flow we needed, and the delta P across of it, of course, too. The turbine scroll inlet shown here is what actually connects everything together. The flange, as you can see, that's welded onto the front of it, welds straight to the flame tube, and then the entire thing slides inside the casing, which you'll see soon, and then it all comes together with bolts. So this piece routes the exhaust straight to the turbine, and then it's attached with a V band clamp, and half of that profile is milled straight into the part, and that was done on Access, and I think it looks incredible. So everything is made of Inconel except for 3 main parts. The Inconel parts are the flame tube, the casing, the inlet, and all of our flanges. And that was given to us by GKN Santa Ana, and we made all of these parts from that because it's both heat resistant and it was a donation, so that was helpful. The swirler, the turbocharger inlet, and the rods that keep all the parts concentric were made of stainless steel 304 because it is also resistant to yielding at high operation temperatures, and it also is easier to machine than Inconel and far cheaper. How it was all made? The flame tube, the inlet, and the casing with the flanges were water jet cut here on campus, and then these water jet panels were sent back to GKN where they were rolled to their proper shape and then welded once again here on the campus. The swirler shell, the vane hub, vanes, and the turbocharger inlet were all machined here on campus with the lathe. The copper gaskets that seal everything in one unit were water jet cut here on campus as well. And then the spark plug tube that housed the spark plug was made here on campus as well. And that was just a simple turn part with internal threads. So it was all assembled with the flame tube, turbocharger inlet, the swirler, the casing flange, and the spark plug tube being welded together as one unit, and that's known as the hot zone or the combustion chamber. And then that will bolt straight to the casing with 5/16" bolts, which is easily seen right there, sort of. And then the fuel ring was swaged onto the inlet with a fitting that was welded straight to the side, and it's maintained with its placement with these retaining rings that you can see there, and it's housed on top of the swirler. And then the entire inlet was welded on top of the entire assembly. And as far as how it was tested prior to being made, a 1/4 scale model was resin printed, so that way it was accurate. And then it was placed in a water flow tunnel where dye was injected, and we verified that there was both swirl and also stable flow through the inlet section. And now I'm going to pass it up to Chloe, who's going to talk about the inlet and our testing procedures.
Thank you, Ryan. Alright, so another component that was designed for this was a ball mouth inlet. The purpose of this was to direct mass flow into the compressor side of the turbocharger. It's this thing right here. It was press fit onto the turbocharger. We considered putting a clamp on it initially and decided against it primarily because it wasn't necessary. It was designed with an entrance area of about 37 inches square, which is what we calculated as what was needed to capture the mass flow needed, and that translated to an entrance diameter of about 8.75 inches. For our full scale testing results, we do have the entire assembly put together and have been able to test it. The combustion was stable for a brief period. However, for the 3 minutes that we were hoping to achieve, we were not able to get there. It was able to complete the combustion before exiting, so the fuel and the air were completely burned before it entered the turbine side of the turbocharger, and we were able to completely spool up the turbo. What ended up happening, we're pretty sure, is that we did not have enough fuel flow. The tank self-pressurization from the propane tank was just not strong enough. We were not able to verify the total temperature of the combustor exit, which limited what we could do as far as data collection. Our engine was not fully running. It did most likely need more fuel input. again, without all of these measurements being able to be taken, we could not calculate our final thrust. We were able to do all of our subsystem testing, so our oil system was fully functional. We had enough flow rate going through the turbocharger that it was not going to overheat and the bearings would stay lubricated. We were also able to test our water system that keeps our pitot tube cool. It did flow fully throughout the pitot tube, and just before turning anything on, you could actually touch the pitot tube and it was almost cold. So we were not worried about the pitot tube burning out with the high temperatures that were going to be exiting the turbocharger. And then a bit about instrumentation. We used mainly pressure transducers and thermocouples along with our pitot tube to try to get our temperatures and pressures. The thermocouples, we used different types of insulation on the wires depending on what kind of temperatures it would be measuring. For our inlet, it was essentially measuring ambient temperature, so somewhere between about 55 and 65 degrees when we were testing was the outside temperature. So we could use essentially any insulation on that. For the combustor was the one that we were primarily worried about, so we used something called XS insulation, which can handle up to about 1500 degrees Fahrenheit, so that we were not going to melt our thermocouple in the process of measuring that temperature. And then similar at the exit, we used a type of insulation that can handle up to about 1200 degrees Fahrenheit, again, to prevent it from melting. For the pressure transducers, we had various types of standoffs that would allow the heat to dissipate between the assembly and it actually getting to the pressure transducer, so that we had essentially no risk of burning out the pressure transducers. And then for the water-cooled pitot tube, it was mounted behind the turbocharger. As long as it was water-cooled, there was very minimal risk of it being damaged, and we do know that that water system did work and keep it cold. As far as attachments, the pressure transducers, we had a combination of stainless steel 304 and vinyl tubing. Again, this partially depended on where it was, what kind of heat we were expecting. For the vinyl tubing, we did put some heat shield tape just in case next to the warmer parts. We weren't expecting it to get hot enough, but we did want to have that extra precaution in there. And then the 3 types of thermocouple wire were used to prevent those from burning out. Along with that, the pitot tube mount needed to be custom designed to hold this U-shaped pitot tube that you can kind of see in this picture. And that just held it clamped down so that it could then be C-clamped to our test stand and hold that pitot tube where we needed it to be. I will now pass it off to Ashley to talk about that acquisition.
Thank you, Chloe. So as she said, I'm going to be talking about data acquisition and processing. So the first thing that we had to look into was how we were going to measure our data. So we decided to purchase a TI Texas Instruments C2000 Launchpad, and this had 21 analog to digital converters where we could read all the voltages off of them. The ADCs connected to the thermocouple wire or to the pressure transducer so we could read the voltages. And the other interesting thing that we had on this board was a reference high so that we could regulate the voltage being measured. So typically pressure transducers read up to 5 volts, but the nominal range for an ADC is somewhere between 2.5 and 3.3 volts, so we needed to expand that range by adding an extra power supply that could read up to 5 volts on the board. So some interesting features that we wanted to add to our interface and to these other hardware that we had was being able to sample the different ADCs at different times. So everything that was connected, we could sample up to 3.45 million samples per second, which since we weren't that concerned about transient response, this is a pretty high sampling rate, but it's nice to know that we could use that much. Every single one of the ADCs that we used had a sample time of 0.001 seconds, and this is so that we could pretty much see if there was any drastic changes even in a short period of time. The other thing that we did was we programmed this board using Simulink and MATLAB. MATLAB is considered to be pretty slow, and I think we should all get that out of our minds because Simulink actually allowed us to have parallel coding instead of sequential coding. And I think this is unique because sequential coding would have actually slowed us down dramatically, whereas parallel coding allows us to read everywhere in the system at the same time. The last part is that the the program was able to save any of our data so that we could use it for analysis later if we wanted to. So here's a couple of flow diagrams of both the entire system from a data acquisition perspective and also another one for code sequence. So the overall data acquisition is the instrumentation emits a voltage, which is read in by the ADCs. Then there's serial communication between the actual microcontroller to a PC or a laptop, which runs the MATLAB code, and upon code completion gives us the Excel spreadsheet and saved data. The code sequence is pretty much how we convert the numbers taken in from the instrumentation and convert it into a way that we can see it visibly from a GUI or a graphical user interface perspective, as well as save the data. So each parameter that was saved in using the ADCs was saved into a structure based off the type of data being measured and where it was in the system. So if it was a temperature or pressure, it would say this is the temperature or pressure at this location in the system, and it would save under that parameter name. Then each individual piece from that structure would go through a safety check and let us know whether or not this was a safe operating range, or if it was in a warning range where we should start to get concerned, or if we should absolutely shut down the system. So this is the simulating software that I use to program the microcontroller. Each pin has its own port and pin number associated with it, so I made sure to include where that was located on the board. I did two interesting things in this code. So the A and C ports actually read up to the 5 volts that we were trying to read for pressure transducers, but because a thermocouple wire only reads in the millivolts range, I brought that down to a 2.5 volt range because it's significantly lower and we didn't need to read as high, so we could actually use those bits for making sure it was more accurate rather than reading up to 5 volts and having significantly more inaccuracies. These gain blocks, and for the thermocouple there's an additional block, those are just so that we can convert the pressure temperature into the actual values because what we're reading is voltages anyways. These are displays. Those were for me for testing so that I could see what was going on and making sure that we were actually getting data as we tested the instrumentation. These last two blocks are ones that I had to make on their own. They pretty much tell us where the operating range should be, where warning range should be, where we should start checking the system if we reach these certain parameters for the temperature and pressure, and lastly a shutdown range, where if it's this high, we should absolutely shut down the system under any circumstances. So this is how we started testing the board, is connecting everything using different color coding schemes. As we usually do in any sort of wiring scheme, make red for hot and brown for black, and yellow or white in this case was for the types of instrumentation. Over here we have the reference connected, as well as over here we have, and here we also have the instrumentation connected. Over here you can kind of see a capacitor hidden. This is to make sure that the board doesn't overheat. When you add a reference voltage for the ADCs, the board tends to get really hot because it's trying to pull more current through, and we didn't want the board to burn up, so we added a capacitor to make sure that this current was being regulated. So this is a test of the graphical user interface that we use. It's black, which is not considered a great thing because it's so dark, but when you're outside and you're testing at nighttime, which is when we had to test, it's really easy to see these colors. So over here I created a legend. So the operation is in green, warning is in yellow, and red is for shutdown. And then the actual waveform was different colors depending on where it was in the system. This was so that we could actually watch it as it came in. And this entire GUI will update every 10 seconds. So we only see 10-second increments at a time. And this is so that we're not watching the entire system and everything's really small. The last thing that's pretty interesting is these two rails here correspond to these times. So we had run one at 2.5 and one at 7.5 so that the values, every time it reached these bars, it would update every 5 seconds. And this is so we could see the current measurement as it came through in a numerical form rather than just watching it on this graph. And these are the safety checks that are corresponding to the original lines that we're seeing on this graph. So if we reach that yellow line, we would end up getting this warning notification. If we reach the red one, we would get this other one on this side. And this is so that while we're running the system, if we reach any of those parameters and somebody isn't looking at that graph, there's still some sort of notification that pops up on the screen and takes priority over the system. And this was so that we could get a notification that pops out rather than just like looking at that graph and making sure we didn't reach those temperatures. So I'll now pass it off to Dylan for test and safety.
Thank you, Ashley. So the test stand is made out of T-slot aluminum provided by 820. This provided a very rigid structure so that nothing was going to move whenever we were testing. We weren't expecting that much to us, but also we were going to make sure that the system wasn't going to move during testing at all, and that way no one got hurt, and that way we all met all the OSHA standards. Speaking of OSHA standards, we met a lot of OSHA standards for industrial experimental engineering. These are just a few ones I want to focus on. We separate our fuel source from the combustor. So our fuel source is located on the base of the test stand, which is fireproof. We use a fire-resistant coating on the baseboard. So if we had any leakage and any fire somehow dig the baseboard, nothing would be combusting on the bottom. We also have many shutoff valves. This one was a primary shutoff valve. This could be operated by the user, which I'll get into a little bit later. Had a handle on it, which the user could shut it off from 2 feet away. We also had inline tank regulation valves, which we could control the mass flow rate of the fuel into the combustor that way too. So, one thing that is being passed around right now is our quick reference sheet and our detailed operations manual. I'll get into this a little bit more later, but we wanted to separate just the quick reference sheet from the operations manual. This way, the operation manual, the users can actually get into the nitty-gritty of what the startup and the procedures need to be, while the quick startup manual just says, check the block, does everybody have their personal protective equipment? Yes. How do you turn it on? How do you shut it off? How do you store it? So we want to separate the two, that way it is easier for the users to operate. In case, a worst case scenario that our combustor did explode, we have a 1/2-inch plexiglass on 3 sides protecting the users. We also had the impact shield glass for the users and any spectators, which we'll get into just a little bit later. So like I said earlier, we had 2 degrees of separation between our fuel source and the combustor, which is mandated by OSHA and the ASME standards. Our fuel source was on the bottom, and the 2 degrees of separation was through our fuel regulation valves and also the vertical distance. The vertical distance helps regulate no reverse flow, and that was also guaranteed by our pressure regulator on top of the fuel source. So for the fuel source, we said earlier that one of our main concerns with why it didn't ignite was that our fuel source was too high, or our mass fuel rate was too high. So to help control that, we had many different types of tank regulations, but these were also to provide no reverse flow and also a quick shut off in case something did go wrong. So for testing, we tested behind building 71. We had caution tape and impact resistant shields. If something did go wrong, we planned to evacuate behind the axe fab and then reconsolidate while safety was contacted and the situation was made under control. We also had individual roles for safety during testing. Zone Alpha is our data acquisition zone, so that is where our computer is, and that's where the battery for our sparker was. And so that way, Ashley can fully monitor all of our values while consistently making sure that we're not reaching our warning or shutdown stages. Zone Bravo was through Chloe. She was more of like our crowd control. So what she did was make sure that nobody unauthorized entered our test stand area, also made sure that everybody was pre-briefed before the actual testing, to make sure that nobody had any questions or concerns and nobody was going to do anything stupid while we were testing. Zone 1 was Ryan, so his primary role was to inspect turbocharger as well as any, and as well as the Pitot tube. He's looking for any leaks, any vibrations that we weren't expecting, anything out of the ordinary on the turbocharger. He is focused solely on the turbocharger. Zone 2 was Anthony. He's looking at the combustor and this system as a whole air system. Again, we're looking for any leaks in the fuel system. We're looking for anything out of the ordinary. Zone 3 was Heather. She's looking at our oil system and anything on our base to make sure that we don't have any leaks or unexpected vibrations. Myself, I was a runner. We had designated kill signs and as well as test signs. So if Ashley saw one of those warning codes that we had, I would give the kill signal and I could relay that back to everybody because they had hearing and eye protection on. They wouldn't be able to fully communicate. I should also note that each of the users was standing 2 feet behind the test stand. Unless they were in zone Alpha or Bravo, then they were at least 5 feet behind the test stand. Our detailed operations and safety manual, I kind of went into it. It's the very deep dive into how to run it, what exactly are you looking for, what measurements are you taking, how do you set it up. So that includes our material data safety sheets as well as our risk assessment. Our quick reference sheet, like I said earlier, is just to check the block. Does everybody have their personal protective equipment? Does everybody have everything they need to get the system running and get cement data? To finish it up, it was going to be heavy.
All right. So we kind of briefly went over this before, but we did successfully complete all of our subsystem testing, although we did not complete testing as a whole. We were not able to run the unit and sustain combustion for 3 minutes. In the subsystem testing, we were able to run the oil system attached to a power source at various speeds, as well as the water pump for our water-cooled Pitot tube. For the pressure transducers and thermocouples, they would all hook up to the graphical user interface, and they were successfully tested that if we were to be able to perform the test, they would read accurate values. We were able to perform multiple hot starts of the full assembly, but all were unsuccessful. They resulted in combustion, but no sustained combustion, and they were not able to actually spool up the turbo completely. In terms of our troubleshooting, while our test was occurring, we were able to do a couple things to see if we could get the engine to fully start. One of these was adjusting the speed of the airflow entering the inlet. We were using a backpack gas-powered blower to direct airflow right into our inlet here. We experimented kind of backing away from the inlet, see if we could slow down that airflow a little bit, approaching it from a different angle. Unfortunately, those did not work. We also tried adjusting the mass flow rate of the fuel entering the combustor using our fuel regulator, which was mounted right next to our propane tank on the test stand. In addition, we allowed some time for the fuel and air mixture to ignite before directing the airflow into the inlet, hoping that this would result in sustained combustion. So in the future, we do have some recommendations if this was ever to be tried again. We would like to increase the hole size in the fuel ring, and this would reduce the flow rate of the fuel. In addition, we would like to research some methods of preventing that blowout condition that we were seeing in our tests. We wanted to plan ahead on getting some more power for the pumps. While we were in our assembly stage as well as our testing stage, we realized we needed a lot more power than we had. So we did have to find some resources to find some higher power supplies. In addition, a printed circuit board for the instrumentation connections would have been really helpful during assembly and testing, as well as scheduling more time for manufacturing, assembly, and testing. This always takes longer than you expect, so we would have liked to plan ahead for this a bit better. Also, increase the smoothness of interfacing between the subsystems. If we had communicated a little bit more as a team, we would have been able to smooth out some of those issues that we actually had to solve during final assembly at the last minute. So in conclusion, we did manage to fully build our assembly and prove subsystem functionality. We also thought it was pretty interesting that we had a fully functional simulated graphical user interface that was prompted the user anytime there was any warnings or shutdown procedures that should be incorporated. And budget and labor hours, we managed to come very, very close to our budget, so we didn't have too many issues in terms of purchasing parts that we needed to assemble the final assembly. In terms of labor hours, we, for the most part, stayed pretty close to our projected. At the end, we did have a spike, of course, at the last minute, where we had to spend a lot of time on assembly and testing. In terms of labor hours by category, by far our engineering hours outweighed our project-related hours. Finally, we did receive a lot of help on this project, so we would like to thank everybody on this list. It's not comprehensive at all, but this is quite a few of the people that really were generous in either their donations or their technical help. So, any questions?
We can just show.
Want me to shout it?
Yeah,
All right. First of all, first you guys, my name is Kenny Young, I'm with Going Mesa, as a licensed engineering manager. Second, during my time span here, prior alum, we had a smaller turbo engine. So way cool that you guys were able to fab something, from scratch. Okay, quick, easy question. You guys selected a specific turbocharger. Was that based upon any set requirements, or was that just like, I can get that off of eBay right now, and I'm taking the buy now?
We kind of had a general idea of the size that we wanted for a turbocharger. Unfortunately, we had a really tight budget, so also it was a cost decision. We were able to find a small mechanic shop that was willing to give us one of their turbochargers at a pretty good deal. So that was mostly us kind of seeing what they had, which one would fit into our project the best, and this was the best fit for us.
Okay, yeah, it was, one of the things I do want to commend you guys on is, first of all, a good explanation of the limitations on like your board, what it can do, what it couldn't do, and some of the things that you have to embed your data. Second, so in the industry, prevalent right now is safety. The fact that you guys look at what are the safety requirements to not just build this, but to safely operate and personnel required. Really good in-depth review, ensuring all personnel are safe, and then also what kind of requirements would be for. Along that line, I want to commend you guys on doing from just my past, a good thorough risk assessment, and using that risk assessment analysis. That's something I've never seen at this level. Typically, I've seen that for aircraft events and mitigating risk of when we have an unknown situation with the likelihood and what kind of consequences. So awesome job on putting that together. Question that I have, and this is kind of a managerial thing. Slide 61, real fast, where you guys are talking about your projected labor and your rates. So I see a very strong linear line. And I know you guys put in a lot of hours to make this happen, but you're going to tell me during the spring break you guys are going to work the entire time.
I believe, if I remember correctly, that spring break was our lowest number of hours.
Okay, so just from an industry standpoint perspective, from a PM, when we look at resources and we're lofting out into time that are prepared performance,
So the inlet is, I guess it's kind of hard to see, right here. The outlet of the oil tank going to the oil pump is right here. And then the oil return to the tank is through this tube here.
You said it was a 5-gallon tank.
Yeah.
How much usable is at the bottom of that inlet outlet?
Really not a whole lot, I would say half of.
Is there any potential in that with that being downstream of the turbine itself to capture and collect contaminant, or does it flush pretty easily just during normal operation?
I definitely think there would be a possibility for some stuff to build up in the tank. How we're using the geared oil pump is a little bit better with stuff like that, and the oil filter to try to filter some of that stuff.
So then on that line, did you give any thought and consideration of oil change interval and then how to maintain and operate that?
Yeah, so we actually didn't give too much thought to oil change interval, just based off of our use would be pretty short with it, but using it for future applications, for long-term storage, the oil would probably be drained and then refilled with fresh oil. So just kind of what we assume.
Cool. So now to slide 22. There was a comment in there, one of the bullets said mass flow required, but you didn't tell us what that actually was. Do you know what you were anticipating for a required mass flow from that fuel line?
Can you repeat that? I'm sorry.
Sure. There's a bullet in there on the fuel line slide about mass flow required, and that's how you decided how to space and size your holes in that ring.
Yeah.
What was that mass flow requirement?
The mass flow was 0.0176 pound mass per second.
Okay. So then in full-time continuous operation, how long would your tank last?
Huh?
So we weren't planning for full-time operation, as we said in our design standpoint, we were planning for 3 megs sustained combustion. And so we weren't,
So thinking more down the road, you know, this is intended to be a test asset. How long is that tank gonna last? Just from an operations kind of perspective. That's something for future groups, you know, if they're gonna wanna use this and leverage what we've done here, are they gonna be buying a tank that we, what's the kind of idea?
I think our,
That's certainly out of the scope of
Just-
what we're looking at.
Just from some quick math, the tank was 20 pounds, and that's 0.01 pounds a second. So if you divide those two out, it's going to be about an hour, I think, or so. Half hour or so, yeah. Yeah, I'm not that great either, but I try my best.
That's a good point, because particularly if that's it for runtime, that's not a long time before you're on the basis. Slide 27. Yesterday during our advisory board conversations, we had quite a bit of conversation around design for manufacturability. So when you put this together, how did it go in comparison to how you expected it to go?
Right. All right. So one thing that I learned personally from all this is that your tolerances need to be checked 5 times over, and so there was lots of shaving and grinding, making sure that all of our parts would slide and just fit properly. That was about half of our time there, probably alone, honestly. But so I learned a lot from that, and I also learned that you have to oversize your weld beads and all that, so that way you leave room for run out, so that way your welds are clean, you can slice them off, and everything will line up properly. But as far as once that was done, the assembly was quite quick, and we got that done in 2 days.
Figure out very valuable lessons.
Yeah.
Slide 31 for the bell mouth inlet. So when sizing that inlet, was there any consideration given to the fact that it's sitting in that case and near that screen? I assume those sizing numbers are based on a free stream input.
They're based on a free stream input. The mesh was added a little bit later, primarily to prevent the possibility of thought. When it was initially sized, it was not accounting for that mesh, But looking at it later, once we had decided to add the mesh, it made essentially no difference, so there was no reason to try to resize it.
And then moving a little farther down the road, you made comments about using the blower. What phases of testing was that used for, and was it intended, was it a startup, was it just a play thing while you were trying to troubleshoot?
So we had always intended to use the blower. It was more to start spooling up the turbo, so it had a little bit of a head start before we did try to start it completely. We found that when we used the specific blower we used, that it was way too much airflow. So it was, in the future, maybe compressed shop air might be a little better, or maybe a smaller battery handheld blower, but it was too much.
Missionary, you electrical engineer.
Yeah.
I had some questions to you because I was way over and up. Jump to slide 51 real quick. This is just a comment, not a question. I would refer to that as a dead zone while you're talking. I would put that up there as a drought zone.
Did they have an opportunity to calculate the airflow through the, I mean, when you measure the color?
That's all I had.
I'm Jeff Jansen. I work at Honeywell Aerospace. I'm a mechanical engineer. I work in the areas of propulsion and environmental control systems.
I mean, the,
I want to compliment you on a great job on the project.
quarter size and stuff, but it.
I want to double down on Katie's comments about safety. Great job. Questions? First of all, on your safety verification, you had two levels. You had like a yellow level that was a warning. You had a red level that said, please shut down. But the shutdown was a manual shutdown, is that correct? So how did you know it won't, I know you didn't achieve it, but at a point in time where you would have achieved it, what was the sequence of operations that would have occurred?
Right, so if you can go to the rolls slide.
To which one?
To the roll slide, the dead zone slide. So I was the runner, and so I was constantly monitoring what everybody was doing. I was constantly in communication with Ashley, and she was looking at the data system. So if one of those warnings popped up, she would let me know, and I would be able to let everybody else know. Since we all have our PPE on, and this is a little bit loud, I was the runner, so to make sure that everybody was on the same page. And once she figured out something was wrong, then I could let everybody else know that we had to shut down.
Okay, got it. So it's a manual process?
Yes.
Okay, as a future improvement, potentially for future, maybe one having an interlock on it, right? So you don't have to, there's no time lag, there's no possibility that the manual process has some type of breakdown. Okay. This is also sort of along the lines of safety. How did you verify the integrity of your welds on your combustion chamber?
That's, honestly, we didn't. I trust my well, Jeff is there in the back, he does great work. We made sure that we're all sealed properly, and I actually did check with Windex and all that, so see if we could see air and all that leaving. But as far as aerospace grade goes, it's like with inspection with radiation and all that, we didn't go that far. But just for
Jeff, great job. Also verify, okay?
Yes, of course.
That's what I just wanted to do. Also, a similar question, you may have answered it, on your ducting and your clamps and your connections, did you run anything prior to spooling up the system at pressure and temperature to just verify from a safety perspective that there was nothing leaking, and if yes, how did you do that?
Tony, want to talk about that?
I would say there was not too many checks before we hooked up the fuel and the oil, but once we're running, well, for the oil system, the oil was put in the tank first, so we actually found a few leaks on some of our tubes, just from the oil being in there. But after pressurizing, a few spots were found, but pretty quickly, and that's how we checked.
We also verified the fuel system too. For the fuel line, we also verified that if there was a leak, then we solved it before we completely integrated everything.
Okay, what about your combustion system, your brake cycle system, as far as any leaks in your
like.
Flanges, yeah, your clamps, yeah.
It was the same spring Windex with what we were putting the blower in the front spring Windex on over the
Not at temperature.
We didn't
no,
want
no,
hot.
yeah, temperature.
Okay, all right, good, yeah, those types of checks are standard, and I didn't read your whole manual, I'm sure it's in there, but it's critically important. Okay, another question, how did you know that your oil was being flowed into the turbocharger to lubricate bearings?
So we actually had some problems with that at first. This oil pump will shut off if it back pressurizes too much. And there's a electronic control valve on the top of the turbocharger that allows oil to flow. And so at first when we were trying to spool it up, it was just turning off after maybe 3 seconds of runtime. And then we found out that there was a restriction at the top of the top of the turbocharger. And so we put in a plug and removed the restriction, and then the oil began to flow. And we verified it by filling up the tank just above the level of the inlet and outlet, and then just did a visual check to make sure that it was flowing through.
Okay, so you know, there's a lot of concentration on instrumentation and your combustor chamber and so forth. If this was in a remote test cell and you were monitoring it sort of virtually, you may or may not be able to, if you weren't able to tell that the oil was actually flowing, what would happen to bearings?
Yeah.
Right, so just think about it in terms of the entire system. You may design the greatest combustion chamber in the world and lose months of time and millions of dollars of cost because of something ancillary to the system that either wasn't checked out or wasn't thought all the way through. I'm not suggesting you didn't do that, but just kind of a lesson learned thing.
Okay.
Let's see. Just a comment on the sequence of your presentation. You had your sort of results of your testing or your experimentation in the middle part of the presentation. Then you did instrumentation, and then you did data processing, data acquisition. Probably a more logical flow is to explain your test setups first, maybe even explain the safety aspects of your test setup, and then ultimately what was the result of your testing. So you want to know, hey, it's just kind of the requirements, the assembly, all the instrumentation, operational procedures, and then the results. That's probably a better way to look at how the presentation will flow. I think that's all the questions and comments that I have right now.
Thank you.
I have a couple of questions. First, about the DAC. How many channels were there actually?
There's 21 channels.
21 channels, and you said it was 3.4 mega samples per second per channel? Okay. And then when you were measuring your thermocouples, you said you reduced the maximum voltage was rated to 2.5 volts?
Yeah.
How many bits?
There's only 12 bits, which I did do a check to make sure it was accurate by doing a couple tests with it before we actually plugged it in. And it was actually reading pretty closely, so I wasn't too worried about the accuracy of the results we were getting. There were a few spikes, and I did some vibration testing by just like shaking it around pretty much. And I noticed it would spike a little bit, but it would still end up reaching a steady state point even at those.
So good, and I'm looking at the rest of you. Do an uncertainty calculation based on the code width of that? Because I know you've all done it, because I've had you in class. So 2.5 volts, 12 bits. What was the minimum? Right, I know. Okay, my last question is, I'm just saying, you have these classes for a reason, guys. All right, so it was stated that you were going to open the size of the holes on the injector ring to decrease the flow rate.
The speed.
The speed, okay, that's what I thought.
Yeah,
Because the
that's what
slide
I meant,
says
yeah.
flow rate. Okay, that's what I thought you meant, so
Yeah,
otherwise.
decrease the speed of
But overall, good job. I really like you guys brought the hardware in here to show people, and this is, I know, a lot of hard work went into this, a lot of dedication. I've seen you guys in there working really hard, doing some really great stuff. So, congratulations. Good job.
So, also, very good job. You guys got really close. The obvious question is, well, how close did you get? You said that you got combustion, but you didn't get 3 minutes. So the obvious question is, well, how long did you get?
Okay, so it would have actually ran for that long. I know it would have. There was a flame staple inside of it, and it was heated up. The actual spark here. If we turn this thing around here. As proof, the spark plug where the hot part is, because there's flame here, is pretty and like blue and all that now. Because it got hot, it was on for a good while, but there wasn't enough fuel to actually sustain. So if there was more fuel, it would have gone off. I have a sound clip of it going crazy. Actually, it was hairline away, but we need like a 3/8 line instead of a 1/8 line.
So it's just pressure drop through the line?
So when propane is feeding, it's in the vapor stage. It needs to evaporate. So when that happens, the propane in your tank will cool down, and then that will cause self-pressing pressure to drop as well. So the actual pressure experienced by the fuel ring was less than anticipated, so the flow rate through was less. It was an overlooked idea that I didn't think of until afterward.
So it was isotopic cooling of the tank, which is leaking so fast.
Yeah, exactly.
Just back how long it's going to run for.
But there was flame. It did get quite hot. It didn't totally start. But it got really loud. It was really cool.
Congratulations, you guys.
Thank you. Does anyone else have questions?